Can I begin? It's okay. Do you have my voice? Yeah, perfect. Okay, let's begin a little bit late. Hello and good afternoon, everyone. I'm Mohammad Tehrani and would like to welcome all in-person and online attendees who are participating in the first edition of Water Whispers Wednesdays webinars. This is a sharing time which is planned to be held a couple of times during the year, sharing the hydraulics and water relevant issues. For those sessions that the speakers will attend in person, the webinars will be conducted in hybrid mode. Each session will feature dynamic presentations lasting approximately 30 to 40 minutes, followed by interactive 20 minutes Q&A session. Before we dive into the talk, a quick reminder to stay engaged. Feel free to ask your question using the chat box for those who are attending online, and we will be back to you and address your question during the dedicated time at the end of the session. Today is no exception and is the initiate date of 2024 series. We have a distinguished speaker who will share his expertise on climate adoption of stormwater systems. Whether you are a senior professional or just a young beginner in this area, get ready for an engaging and informative session. Without further ado, let me introduce our esteemed speaker for today, Dr. Salar Hayat Afshar. Sure. Salar holds a PhD from Lund University, Sweden. His dissertation focused on the monitoring, modeling, evaluation, and optimization of blue-green stormwater systems. Currently, he works as a project manager at Sweden Water Research, focusing on the enhancement of urban water planning and design paradigm in urban to face the challenges of an uncertain future. Solar interest area includes the application of AI and machine learning techniques in the field of urban drainage. At Sweden Water Research, Solar has the primary responsibility for two projects. Firstly, the company's contribution to Mirza Inframed Phase 2, which focuses on the climate adoption of the urban stormwater drainage system. And secondly, the R&D collaboration on the use of X-band radars in the Öresund region, covering regions in both Denmark and Sweden. He is investigating how water can respond to the climate change and challenges with respect to the planning, design, and management. Salar has also part-time employment at Lund University to supervise master thesis and PhD students. He is a coordinator and the main lecturer of the course Urban Stormwater Management at Lund University Faculty of Engineering. Salar, thank you so much for accepting to be with us. The floor is yours.
I will share my screen before you start.
Sure.
Thank you for the introduction, dear Mohammad. First and foremost, I want to express my gratitude for your invitation. You personally and also the University of Toosi. It's a pleasure to be here. I feel really honored by this occasion that you provided me. So today I'm going to talk about adaptation of urban drainage networks to changing climate and city. So most of the time, within the research community or practical community, we talk about climate change. But we miss the point that not only climate change, our cities also change during time, and we are not really equipped to meet that change. Urban drainage is not a new issue. Human beings, since very early civilization, they have realized that they need to drain their cities and they need to keep it dry. That they have had the same issues that we have today with regards to rainfall. Here on the left side of the screen, you can see drainage systems from a very old civilization in the Indus Valley. These sites, archaeological sites, are nowadays located in Pakistan. And this is, of course, our famous Adaptation. And this is drainage channel that goes through the site. So this is an ancient art, to drain the cities. It has been around for as long as humans' history. The problem we have today is that we face more and more frequent flooding all over the world. It's not only an issue in Europe, it's not an only issue in Iran, in Ahvaz, for example. It's not an issue for Sistan and Balochistan province. It is happening all over the world. And this is the statistics that I have taken from the United Nations Office for Disaster Risk Reduction. As you see here, since 1980s up to 2011, the number of flooding events globally has increased dramatically. And of course, I think I should take this opportunity to talk about the terminology floods, because we have different types of floods. We have coastal flooding, and I think all of those coastal flooding are also included in this statistics. We have fluvial floods or riverine floodings, those caused by the overflow of riverbed because of the high river flow. The third type of flooding that is kind of the subject of this seminar is called fluvial floods. And these fluvial floods are those that are caused due to overwhelmed drainage network. So you have a city, you have a pipe network that lies under the ground, or you have a channel network that lies on the ground. You have a rainfall that exceeds the design capacity of those systems and leads to flooding. When I say flood from now on, I mean fluvial floods, not coastal flooding, not riverine flooding. Although some of the ideas and concepts that I'm going to discuss today could be applicable for all other types of floods as well. So this is the problem we have. We have increased floods all over the world, but why is that? Why do we have these increased frequent floods? Is it only because of climate change? Could be. But we should also think about the fact that during the past 40 years, not only climate has changed, but also our cities have also changed. During the past 40 years, we have had an intensified urbanization. People have moved from rural areas to the cities. We have paved larger and broader surfaces of our cities with asphalt, with concrete, and all of those add to the increased runoff in the cities and exert a huge load on the existing drainage network. Wrong direction. Yes. Some context. This study was published by Tehrani et al. In 2012. This is a study from Denmark. And I like this approach, which is called three-point approach, because it adds some context to all our discussion. According to Tehrani and their three-point approach, we can classify rainfall into three different categories. We might have a little rain in our cities, which occurs every now and then, quite frequently. So it's an everyday phenomenon, yes. When you have a little rain, what concerns you is your day-to-day values. You don't fear your life. You don't feel threatened. You don't feel that you are going to be damaged by that. It's just a matter of your day-to-day values. It's your day-to-day routines that might be affected. The next level of rainfall is the level of design rain. That is the rainfall that we design our drainage networks for. I don't know how it is exactly done in Iran, but in Sweden, for example, we used to take 10-year rainfall. Nowadays, we use 30-year rainfalls. That means the rainfall that is expected to occur once in 30 years based on the statistics that we have historically had. So this is the design rate, and this is the domain of technical optimization. of the water system. Your city needs to be able to handle that level of rain and be dry, still be dry. The third type of rainfall is the extreme rain. When extreme rain comes and falls on our cities, it's no longer a matter of drainage. It's a matter of urban resilience. Sometimes, quite often, I see on LinkedIn or other social media that they share videos of very extreme flood events, and they say this is a sign of a failed drainage system. It is not. That rain, if it comes, there will be flooding. You cannot avoid that. The flood will be there. It's not a matter of drainage. It's a matter of urban resilience and spatial planning. In this domain of extreme rain, you need to save your citizens from being drowned and killed by the flood. That should be the priority, not keeping the city dry. You see, the priorities change as the domain of the rain, or the class of the rain, or the type of the rain changes. So, what challenges do we face today? Of course, according to some studies, we have no more stationarity in our climate. I will talk about that in the coming slide. We don't really know what shall we adapt to. We have an intensified urbanization process, and we have had that process changing urban landscape. We have a city today. We design drainage network for that today. We are not completely sure if the circumstances will be the same in the coming 10 years. The urban landscape changes all the time. Maybe a new football field will be built somewhere, which adds to have a larger permeable surface. Maybe a football field will turn into a parking lot. Then you have eliminated a huge pervious surface and change it into a impervious surface, and that changes your urban hydrology. For those cities that are located close to the sea and ocean, we have an issue with the rising sea levels. Of course, rising sea level exacerbates the situation with coastal flooding, but it most of the time affects the urban drainage network as well, because in coastal cities, the stormwater is drained into the sea. The network is connected to the sea, and as the sea level rises, your network capacity is also impacted. You have less capacity in your system for the drainage. Unclear borders of responsibility territories. We had those three different classes of rain. In many countries, there are different units in the municipality or in the city that take care of those things. But still, it's not 100% clear who is in charge of what. Of course, maybe the water utility company says, I am only in charge of the drainage system if the rainfall intensity is up to a if the intensity exceeds that level, I am not the responsible person, it's someone else. But who? I mean, all these discussions, these are valid discussions all over the world. And people are talking about these territories of responsibility when it comes to the management of stormwater. Limited economic capacity, that's an issue. Even in the rich countries, that's an issue. We always have limited resources and limited economic capacity. We cannot expect that our country invests all its capital into our drainage system. Countries need to take care of healthcare, the school system, the transportation system, and so on and so forth. So the share that is left for the drainage network and urban resilience, let's say, will be a limited one and a small one. We have limited resources. economic resources, as I said, but we also have a problem with competence and expertise. The more complicated our societies become, the more collaboration between different people of skill is also required. And we need to link these people together in order to solve our problems. If you are a good urban hydrologist, you need to collaborate with probably somebody who can GIS, probably somebody who is a good economist, somebody who is a good architect, urban planner, in order to solve the issues we have today. So water management in itself, in its silo, is not enough to face the challenges that we have. So we need to educate competent people and provide an environment so that they can interact and collaborate with each other. The last but not the least is the lack of public awareness, responsibility, and sometimes unreasonable expectations. That's a problem, and that's a problem all over the world. As I said, flooding is a disaster. You can mitigate its impacts, but you can never avoid it. Sometimes people expect that as a city, you are responsible to keep them 100% dry and safe, even in case of a very extreme rainfall. That's unrealistic. That would never happen. There will be flooding, just like there will always be earthquakes, right? What's the matter? I mean, the issue, when you have an earthquake, the expectation is that you need to do some things. You need to train so that you are alive. The same applies for urban flooding. I mean, if you have a very extreme rainfall and your city is flooded, you need to communicate with your citizens, the people of the city, the inhabitants, so that they are trying, they are well informed what actions, what measures they need to take in order to save their lives and their family's lives. We need to look at flooding as a kind of natural catastrophe rather than a system change. That's one of the points that I want to bring up in this seminar. In 2008, this study was published in Journal of Science, which is a very known, well-known scientific journal. And the authors of this article, they claim that stationarity is dead. What should we do with the water management? What does it mean that stationarity is dead? Stationarity is dead means that up until today, up until the climate changed, our rainfalls were expected to fall always between a certain range, right? So it has a constant mean, so it always occurs. It has a mean level of 0, and it has a very constant variance over the time. So, what did we do with this stationarity? We invented the terminology of return period or recurrence interval. How? We said that, let's say that we want to see, let's say that this is the rainfall intensity, and here we have an intensity that we want to design or find out the return period. You look at your historical data, you identify all those peaks in your data, and then you say, okay, how often do they occur? And in average, you define the return period. That was the nice thing with having a stationary weather. But if the stationarity is dead, according to MIDI, this is how our time series will look like in future. This is a non-stationary time series. And in this non-stationary time series, you can no longer define the return period. So we have kind of dived into a unlimited uncertainty. It's like 100% stochastic and uncertain. We don't know what's going to happen. We don't know even the levels of the rainfall that will fall in the future. In 2000, And 11 or 10, it was 2010, we had a very extreme rainfall in Copenhagen, Denmark. According to some rain gauges, the return period was extrapolated to 1,000 years, even though it's unrealistic because we don't have data for 1,000 years. But if you extrapolated it, that would become the return period. So we don't really know what's going to happen. So we have a very deep uncertainty to plan for. The idea of return period is based on probability, but there are some problems with probability as well. As I said, urban water management requires communication with the citizens, with the inhabitants of the city. And one of the problems with probability is that it is very difficult to communicate. It is prone to misinterpretations. Here are some examples, right? Perceptions of probability based on recent experience. Some people say, we have never had that in our neighborhood. We are safe. Because it has never happened, the person thinks that it will never happen. Right? But when it happens, the same person would say, flood mitigation should be our top priority. The same person. The second impact or cognitive bias is gambler's fallacy or negative recency. What does it say? The person would say, we just had a flood. We will be safe for some time in the future. They think that if you have had a 10-year rainfall today, you are safe for the coming 10 years. No, that's not how probability works. If you had a 10-year rainfall today, you might have a 10-year rainfall tomorrow. The probability doesn't change at all. These are the problems with probability-based design. So what should we do? We have a huge uncertainty, and we have a changing climate and changing city. I think, and the people I work with think together, that a possible way forward is to continuously, this continuity is the key word here. We need to continuously map and monitor flood-prone areas. We need to know how this flood landscape changes in our city all the time. So we need to find a system to monitor our city kind of online, in real time. We also need to quantify flood consequences, right? We need to have consequence maps. Keep in mind, if you have flood area, it doesn't necessarily you have had a top and large consequence there. So being flooded in itself doesn't mean a bad thing. I mean, if you don't have a huge damage caused by that flooding, okay, let it be flooded. We don't have a problem with that. The problem is with the consequences. The flood map and flood consequence map, they don't really overlap all the time, 100%. They change. We need to communicate the concept of flood risk with politicians, individuals, and private landowners. We need to educate our people, and also our politicians, that this is an issue we have. The flood will happen sooner or later, and we need to prepare for that. And we need to take responsibility. It's not only the responsibility of the municipality or the responsibility of the government, but it's the responsibility, the collective responsibility of individuals, of private landowners as well, to keep themselves safe in the situation of extreme events. We need to solve targeted optimization problems to reduce risk in locations of importance. And my argument here is that the municipality as a public entity, it has to focus on essential services and critical infrastructure. As I said, we have limited resources. We cannot keep 10 million, 12 million, 14 people, individuals, by those limited resources all the time. What we need to do is that to make sure that the essential services in our community and the critical infrastructure is safe. What are these things? Like hospitals, police stations, nursing gardens, power plants, you name it, right? To keep the infrastructure safe and intact, you allocate your resources to mitigate the risk in those areas, and then you educate your community to take actions on their own. Of course, this is open to criticism. This is not, it's not the page from Bible, as the Europeans say. It's not the verse from Quran, so it's open to criticism. So anyway, continuous modeling and monitoring requires fast and representative models. If you want to monitor your city all the time, you need to have a reliable model that works quite quickly, so that you don't need to wait hours or weeks to run a simulation. That's the issue that we want to tackle. So this, up until this slide, it was a kind of a introduction. In the coming slides, I will talk about some concrete projects that we have in line with this aim that I have introduced here. One of the projects that we work quite intensively and extensively on is the implementation of X-band radars. These are weather radars that can be calibrated to measure rainfall. Traditionally, we use these rain gauges. These are tipping bucket rain gauges that measure rainfall in a very specific location. If you use the data from a tipping bucket, most of the time you assume that the same rainfall is valid for a larger region, but that's barely the case. Using radars, what happens is that a point measurement turns into a distributed measurement. So you have measurements for the broader area for the region. A very nice thing with X-band radar is that they have a very high resolution of measurements. You can get one measurement per 500 meters times 500 meters blocks in your cities. And it could be decreased to 100 by 100 meters blocks. So it's quite interesting. So what do we do with these measurements? X-band radars, you can cover an area of 100 kilometers in diameter. Is 500 by 500 meters, and it could be downscaled to 100 times 100 meters. It requires careful calibration. You need to put quite a lot of time to calibrate your radar to get the right or fairly precise measurement. More reliable if two or more X-band radars are combined. So if you have only one X-band radar, the data that you acquire from that probably is not the best data that you can achieve. But if you have two or more X-band radars covering the same region with some overlap, that would be the best case scenario. Why? Because sometimes you have problems with shielding. One radar cannot cover some specific regions or areas. In those cases, the second or the third radar will cover them. There's another problem in case of very intensive rainfall. If you have a very intensive rainfall with a very intensive core, the radar beam cannot penetrate through the core of the rainfall. So you miss the data on the other side of the rain front, right? So that's why it's good to combine these systems. These are the error sources that you need to think about when it comes to radar. Because the beam that is radiated from radar, it doesn't know what is rain. It just collides with any objects sky, and it reflected back to the radar, right? And those objects could be insects, could be birds, could be airplanes, could be chaff, could be anything. This is the hay effect, that's what I said. But you might have problems with overshooting, you might have problems with shielding, ground cluster, etc. You need to find out to teach what is a rainfall and what is not a rainfall. That's the challenging part. This is what we have been working with. So what we work on today when it comes to X-band radar is that we are studying the combination effects of data from 2 or more X-band radar. This is the where I work here, right? So this is my city, Lund, and we have a radar very close by. And this radar has a diameter of a coverage diameter of 50 kilometers. We have a second radar in the city of Helsingborg in Sweden, and it covers a diameter of 70 kilometers. And we are studying this overlap area to see what kind of improvements do we get from this combined coverage. There is another thing called micro-rain radar. And micro-rain radar sends its beam vertically to the sky. And it's drop size of the rain at different stages, because the size of drops change all the time. Rain occurs in a layer close to the clouds, and it's in the crystal form. At some elevation or altitude, it is melted and it changes into a drop, and you want to monitor all these changes along the way, from the moment the crystals melt till the moment it touches the ground. And this is required to calibrate your radar data. So you need to combine micro-rain radar with the normal X-band radar. List of companies and organizations who are collaborating in this project. Of course, this is the company I work for at. This is the university that I also teach and I have graduated from. This is a water utility company for the city of Helsingborg, and this is the water utility company for the city of Lund and Malmö. And this is the Swedish Meteorological and Hydrological Institute. So it's like, the weather organization. I would like to take the opportunity and introduce my 2 colleagues who are accidentally also Iranians. Hassan Hosseini and Hussein Hashemi, who are researchers at the university. These 2 gentlemen work with remote sensing when it comes to urban hydrology. So Hassan is focusing on the X-band radar and micro-rain radar, but Hussein works with broader topics, including satellite information. Introduce them and acknowledge their contribution to this presentation. The second project is about surrogate model for network hydraulics. In 2011, we published an article. This was a study, and we were wondering where in the city should we implement blue-green infrastructure so that we can relieve pressure from the existing network in an optimized way, right? Depending on where in the city you implement these blue-green retention infrastructures, it has different impacts on the hydraulics of your networks. So we want to optimize it and find the optimum location for the implementation of these systems. So we divided our city into 30 catchments, and it was a combined sewer system. Total drainage area was 954 hectares It was a huge catchment. The network that we studied had over 2,600 nodes and more than 160 kilometers of piping. What happened in that study was that because for optimization you need to run simulation over and over again. You need more and more iterations. What we managed to do was that we could run only 325 iterations, and it took almost 100 hours. This is not a feasible way. St. Bennett equations, right? And those equations take quite a lot of computation power, especially when you're working with a city-scale catchment. You have 2,600 nodes. A 10-year rainfall could take maybe 10-15 minutes to simulate. So if you want to run an optimization algorithm that requires maybe thousands of thousands runs, that's not the way to go. It's almost impossible. Not almost, it's completely impossible. You cannot do that. So you need to use some kind of local optimization algorithms. And that's not really the answer. Answers turned out to be quite silly and meaningless. So the challenges we had was that the target optimization space was quite huge. If you only want to adjust two parameters, you have a two-dimensional optimization space. In this case, we had 30 samples. We had a 30-dimensional optimization space. It's unimaginable. It's very complicated. Larger study area has a strong impact on computational expenses. So that's what I just said. So the methodology was not really suitable, as I explained. So we thought we could do something. Traditionally, we had introduced our rainfall theories to our catchment coverage. You have an area, you have a runoff condition, and you can calculate the runoff for each catchment. And those runoffs, they are combined into a model and are translated into hydraulic properties of your network, like flowing your pipes or the hydraulic head in your nodes, etc. We thought, because this is the most time-consuming compartment or module in our model, we thought maybe we could substitute hydrodynamic engine in our models, the machine learning engine. We could train a machine learning model who could take these runoffs from each sub-catchment and the same hydraulic properties of the network. That would be a very, very interesting advancement to study, because 20 minutes of simulation will turn into a second, probably. But these are data-driven models. They're very easy to solve. And we did it. We said, okay, let's give it a try. Don't try, we will never know. We used a wavenet structure, and this wavenet structure is something that is kind of developed by Google. And we implemented it utilizing Keras and TensorFlow, and we translated the rainfall time series and runoff time series into network hydraulics. Okay, how good? The quality of the data or the results I'm presenting in the next slide, but this is the assessment criteria we have. We use Nash-Sot efficiency index, and we have color-coded them. So for a very good efficiency, we use the dark green color, good, satisfactory, unsatisfactory. Of course, if it is equal to 0, the original Nash-Sot clip, then it's as good as the mean. That's the explanation. And if it is below 0, it's worse than the mean. So this is the criteria we have. And we did this on a network with over 1,000 nodes. So it was still a big turned out to be. You see, if we group together very good, and satisfactory, and say that's the level that we like to have, we have achieved satisfactory level in almost 66% of our nodes. But the remaining 34% of our nodes, they are still problematic, right? They are not so satisfactory. And you see here, we have 16 nodes that the model has not been able to predict. Those lie in this pinkish area. And we have quite a lot that lie on the unsatisfactory area. Just to give an example how it looks like, this is the time series that is predicted at a very satisfactory or a very good level. So the red line is the prediction by the machine learning model, and the black line is the original data set. Here we have listed the D, but the other parts of the time series has been predicted quite well. And this is one of those unsatisfactory predictions. So, I don't say this is perfect. 66%, I mean, you win quite a lot of time. Instead of spending, I don't know, 100 hours, you are done within 5 seconds, but it comes with a compromise. And the compromise is that you only achieve good simulation or acceptable predictions in only 66% of your nodes. That's something that needs to be improved, and we are working on that. So we have radar, and we have this kind of models that we work with. The next step seems to be very obvious, combine these two together. Because radar data, of course, you don't use radar just to measure rainfall, you want to use those measurements. And one of the uses is that you want to improve your hydrodynamic model. Right? Instead of using one set of time series achieved or received from one tipping bucket rain gauge, if you could just use distributed rainfall data, you significantly improve the quality of your simulation. So that is kind of the next phase. What we want to do is to take the data from Expand Radar, adjust our hydrodynamic models, kind of translate Expand Radar into hydraulics of our network. We'd also like to include sea level data in our machine learning models. And then at the end, we also need to think about the flood consequences analysis, right? And run an optimization. Of course, this optimization, I have made blue-green infrastructure both because when it comes to uncertainty, you need to be flexible. You need to be able to change what you have implemented today within 5 years or 10 years. And blue-green infrastructure, they have this kind of flexibility. If you excavate your streets and dig a pipe with 700 millimeters diameter, and then you cover it and then you asphalt it, it will be very difficult in the future to change that one. It will lie there forever. So those kind of measures that are hard to change, they are called locked-in measures. You are locked in there. You cannot change it. You cannot modify it. So it is good to think about flexibility when it comes to science adaptation, also continuity. Able to continuously monitor, make modifications where needed, and that's why these kind of infrastructure, they are more preferable over locked-in measures. Of course, they are preferable, but we should not limit ourselves to only blue-green infrastructure. We should always take the opportunity to use also pump stations if needed. We also need to consider the option of replacing the existing pipes with larger pipes. live in an uncertain future. Dealing with uncertainty requires flexibility. So we need to think when we design solutions, we need to think ahead and say, okay, what if I need to change this? Public and political awareness and understanding is definitely needed. Even if they do not contribute, they need to be aware of the facts. Drainage capacity shall be distributed in accordance with risk landscape. We don't have enough resources to provide same level of service for a city of 15 million. That is unreasonable. We need to select locations of priority, locations of importance, essential services, and try to focus on them and educate our community so that they can take care of themselves in case of extreme events. Continuous monitoring and simulation is the key activity in the adaptation process, and of course, use of artificial intelligence and machine learning combined with radar data, it opens up new opportunities like global optimization algorithms that we never could use before because of the limitations with hydrodynamic models. With that said, I thank you again, and I'm ready to listen to your feedback and discuss potential questions that you might have. Thank you.
Thank you so much, Salar, for accepting our invitation to being here with us today also in a limited time that you are visiting Tehran again. Thank you so much. Nice of you. Thank you. Your favor. So now it's time for some potential questions here. Just I was wondering if I can say something for ice breaking, but the first is Karim. Yeah, go ahead, please. No, it's okay. But please, those are here in the room, please turn on your microphone so that the camera and the audio system will recognize your voices very well, so that those are attending online will hear you as well. Please, go ahead, please.
Thank you for your presentation. It was great to hear from you, your experience. I think these experiences can well fit with our cities and systems. My questions are falling into different categories. I'm not sure how should I proceed, but
and I'm not sure if I have the answer to your question.
No.
So just feel free to shoot. Yeah.
So I'm gonna start from the end. Like you talked about, like in one of your very last slides, you mentioned about the sea level data going here goes to your model. Your coastal, Sudan coastal cities are near northeast, right? Am I sure? Yeah. So you're experiencing high tide range, right?
No.
And one of the main issues with this sea level changes is nuisance flooding. So, and then the waves and the water that can be added to what you have already with the rainfall, those can exacerbate the flooding. So, I would like to hear a little bit about, like, if you know what they are doing with this nuisance flooding. Do they have any planning for the future? And this is my first question. Should I ask the others and then you answer, or one by one, whatever you
I will just give you a short answer regarding the coastal management. I mean, what I know, I've not been so active in that field, so I don't have the correct answer to tell you. But I know that the department or the division of water resources engineering and also at authority level, they have had very huge projects with respect to sea level say, coastal conservation or, on the coast of Sweden. When it comes to the modeling aspect, that is a tricky issue because you need to kind of introduce a kind of, how to say, border limitations to your model, because your outlets from your drainage network are going to be delimited by the water level, and that has an impact. We have had so far one project that has tried to model the drainage network with respect to the sea level rise, because we have the sea level as the recipient of the drainage network. We still have the problem of high computational cost when it comes, because you make your models more complicated when you add such kind of border criteria. So that's something that we are working on at the moment. I don't know if I gave the right answer to you.
Yeah, I mean, yeah. So are they gonna change the infrastructures with these blue-green things around the coastal cities, or, you know?
That's a very good question. We have an issue when it comes to implementation of blue-green systems. And the thing is that, as I said in one of my slides in the beginning of this presentation, that's the responsibility territories, because these are both infrastructure and also elements of urban planning. So who needs to pay for them? Who needs to take care of them? That's one issue. The second issue when it comes to blue-green infrastructure is that most of the time there are several landlords in a neighborhood. And it makes it unimaginably difficult to come to a kind of decision to implement a blue-green system if you are 3 or 4 different companies involved within a limited neighborhood. We have had a very nice example in Malmö, in the city of Malmö in southern Sweden. It's a neighborhood called Ostad, and they have retrofitted the entire area, the entire neighborhood, into a blue-green neighborhood. The nice thing with that huge neighborhood was, or is, still is, that it is owned only by one company. This is rarely the case in other neighborhoods. So when it comes to implementation, we have a problem. All these kind of developments that I present here, radar data, optimization modules, application of AI, etc., etc. Of course, this is at the development phase, but we need also at the same time build organizational capacity so that these new findings or tools are really used in practice. Because there is, how to say, if our systems are used to their routines and procedures, and it is very difficult to change that. We are used to use, for example, Mike Urban models. I don't know if you're familiar with that model, Mike Urban or SWIM. If an organization has used Mike Urban or SWIM for the past 30 years or 40 years, it will be very challenging to ask them, just put it aside and use my new methodology instead. That will take time. And that is something that needs research and needs projects to be done so that you also build an organizational capacity at the same time, at the same pace as you make these developments as well. So making a development is one thing, getting it to be used in reality, in practice, is something else. And it requires other types of actions and measures. So they don't always move at the same pace. Sometimes the practice lags behind, and the research and development goes ahead. And this is a problem. And it is a problem in Sweden as well. But this is something that we are working with all the time.
Good point. Like, I mean, this is the point that I'm gonna move to my next question if you allow. It's you talked about this different entities that needs to work together about one thing, and this is kind of a system of systems, planning projects and those kinds of things that it's not a problem just in our country. We hear that it's in all of the developed countries too. So you talked about the public education in your slides, and that's one of the points that we engineers are always miss. Like we miss that whatever we are producing should be used by politicians, by public, by people, and we need to educate them. It's not the end of the story. You design it, and that's all. We need to educate people, and we need to collaborate with humanity scientists. So I myself had this problem in, like, when I was at Louisiana. There were people who were living near the coast, and their land were sinking, and they even the politicians tried to persuade them that to evacuate those areas, and they don't even they see what's happening. You talk that the people see that flooding, some of the, but these people were seeing that their lands are sinking, and they stayed there because they were telling that these are our father's lands and these are our lands, and we never go. And we have such problems with water consumption in our country, and like agricultural productions and those kinds of things with the drought. So it would be great if you tell us about your experience with this kind of public education, how Sweden is dealing with this to communicate these modeling or engineering findings with people, and how they accept that, and
Yeah,
that's all.
that's a very to the point question. It's really on spot because traditionally universities used to have two responsibilities. That was education and research. I think that's the same here, right? Since several years ago, we in Sweden received a third task as a university. So we work with not only education, not only research, but also with science outreach. What does it mean? It means that we are obliged, asked by law, to disseminate our research in very simple words and language to the public. We need to talk about the research we make, or we do at our universities, with the public, with ordinary people, and make them aware of what's going on in our university. Another good example is that, so how do we do with these science outreach? Yeah, we have different platforms. You could, as a scientist, write popular science articles and publish it in ordinary newspapers. You don't have to publish it in scientific journals. Yeah, of course, that also is required, but you also have an obligation to reach the public, reach the ordinary people, and talk about and present your research. Another thing which I find very interesting in Sweden is that every now and then we receive invitations from schools, primary schools, and they ask us to send researchers, most of the time PhD students, but also some senior researchers as well, to go to the school and talk to the children at the school, to the students, and then introduce them very basic principles of water management, for example. Where does the water come from? Where does it end at after we use the water? What happens to that used water? So these are the things that I think are highly required to pursue all over the world, including our country. We need to have, over the lunch, I and Mohammad talked about collaboration with the industry. That is something that I remember has been around for at least 20 years, maybe more. We had an office at our university in Tehran, an office of collaboration with industry, but we had an office of collaboration with schools and collaboration with the community. Those are the puzzle pieces that we miss today, and we need to add them to our puzzle so that we could have the working and functioning community. Otherwise, all these tools and developments and advancements, of course, they will nice, they will bring me academic merit. I will have higher H index or whatever. But to make an impact, you need to reach out. You need to talk to people and educate them and make them aware of the mistake. Yeah, thank you for the question. That was really good one.
Thank you so much for the nice question and brilliant answers as well. No?
Thank you.
Okay, I will come back to you. We have a remark, let's say, from one of those attendees online. If I can find it, yeah, Mr. Abul Qasim Akbari. I just would like to share his comments on your talk. He wrote, thanks for sharing your experience in design of radar-based urban drainage systems, but we do not have radar technology in Iran. So he doesn't continue, but I guess he's asking, what shall we do even without the radar technology? Just to make it clear, I think we have, but just please.
I also think I don't want to share my thoughts, especially when we are offline. But if as soon as we are offline, I could give you some comments. I realize the problem. That has been an issue with my colleagues who are working with. They didn't have access to laser using.
Sorry, just to add, sorry, because he now is writing not enough radar network. It was what he meant, not enough radar network.
Not enough radar network. One of the things that one of the projects that also is going on in Sweden, I'm not personally involved, but that's a quite interesting one, is to use mobile masts to monitor rainfall. Because the same thing that the radar does, the same thing these mobile antennas or masts, they also do. So depending on their signal quality, when it rains, you can translate that change in signal quality into rainfall intensity. That's a project that has been successful. The problem with that project is that it is too expensive. Why? Because mobile networks are owned by private companies, and they ask for a lot of money to make their data available. If you do not have X-band radar in Iran, you have mobile networks. I know at least one of them is owned by the state. That could be a solution.
Thank you so much. I hope that Abul Qasim is happy with your answer. Let's go with you. Please turn on your microphone and then please turn it off so that the camera will go back to the presentation and Solar as well.
Yes, I can ask.
Yeah, sure.
I had a question regarding your machine learning model you've been using, and you've shown a few charts in there. The machine learning, the chart that showed the results for the machine learning. The different, yes, this one. My question is basically at the beginning of your presentation, you showed a chart that regarding the stationary time series, which is basically that it's no more applicable at this moment. My question is, in order to develop a machine learning model such as this, what kind of data have you been feeding to it, given that we have such variations in the future? And so how exactly what kind of data have you been feeding to it in language?
Very good question, very relevant. In this specific study, because we looked at this as a kind of proof of concept, we just wanted to see if it works. I mean, at any tension. So we fed our model with 3 months of rainfall data, and this 3 months of rainfall data didn't have any dry periods. We actually removed the dry periods from the time series so that it was kind of compressed into 3 months. On top of those measured rainfall data for 3 months, we also added some design rainfalls, CDS rainfalls, Chicago Design Storm. I think we added a 1-year rainfall, a 10-year rainfall, and 20-year rainfall. 1, 5, and 10. We are writing an article based on that, so I can share the article with you as soon as it's published. But that was the amount of data that we used. I'm aware that it's not enough. Usually, if you want to have a very good AI model or machine learning model, you need to use a lot of data. And those data needs to be very diverse. So you need to introduce a lot of variations into your data so that you cover the entire modeling space. But in our case, it was 3 months of wet weather data, kind of enhanced with design storms, 1, 5, and 10-year storms. That was what we used.
Okay, yeah, sure. Let's turn it on.
Hi, Dr. Hayratur. I appreciate your great work and nice presentation. I'm a water resources graduate, and I have a question about the time series you show. We know that most of the hydrologic time series are non-stationary. And I have a question. What's your opinion to use detrending? Because it
What?
use detrending.
Detrending?
Detrending instead of a non-stationary analysis, because it really reduces the amount of calculation. What's your opinion? And
I'll be 100% honest with you. I'm not a time series expert, so I'm not really familiar with those terminologies. I think perspective I have, and I also talked about it in this presentation, is the uncertainty aspect that we have. Right? I mean, you can do whatever you want with your time series. You can transform those non-stationary time series into stationary time series. You can work with them. You can use untrending, as you say. But at the end of the day, what we have is an uncertain future when it comes to the climate. And we need to plan for that uncertainty. Of course, all of these will impact the level of design range we decide to design our network. But no matter, regardless of the fact, what design level you decide for your network, you are going to deal with uncertainty anyway. We talk about, maybe, I don't know if I answered your question, but just an additional point. Most of the time we talk about 100-year events. We say that flood is like a 100-year rainfall. If we adapt our cities to take care of a 100-year rainfall, then we have adapted our network to these climates. But nobody talks about, first of all, where does this 100 come from? Why not 95-year rainfall? I mean, where does these numbers come from? 10-year rainfall, 30-year. Nobody talks about 33-year rainfall, for example. It's always like a multiple of 10. 100-year rainfall. Okay, let's say you have a system that can take care of 100-year rainfall. But as soon as you have a 105-year rainfall, then it's done. So that's the kind of problem we have. So no matter how high you raise your base level in design, you will still have uncertainty on top of that. So you need to deal with that uncertainty anyway. Sorry that I didn't have a good answer for you. Yeah, but this is how I look at this issue, personally.
We discussed the uncertainty related to future changes and climate. I'm just curious to know if you use the uncertainty for prediction because it's very important to know that our prediction is reliable or not, especially when the early warning of the flood is important and we want to know about the early warning data to our prediction.
Yes.
Did you use in your work?
Not me personally, I have not used that, but I get the point, what you say about what you say. It is, of course, you have to quantify the uncertainty. The more deep into the future you predict or project, the uncertainty increases, and that's the kind of perspective we always have. The more deeper into the future you go, everything gets more uncertain. I think when it comes to the design of your networks, because even though we have a huge uncertainty, we still need to design something and implement in our city. We need a drainage network, and for that drainage network, we need a level of service. Even if I claim that we don't have return period as we used to have, but we are stuck with that terminology, I think, for some decades here. We need to use that, we need to predict the uncertainty, we need to quantify it, we need to make engineering assumptions to have a functioning or hope for having a functioning system. I think at the implementation level, we still need to work, as you suggested, we need to quantify the uncertainty, we need to have a base service level, we need to have future scenarios, we need to predict how the climate would look like in 20 years, in 50 years, in 75 years. All those predictions we need to make, we need to quantify and work with. But in the back of our minds, we should also be aware of the fact that all of these are projections, not necessarily true. I mean, if you make a projection for the next coming 50 years, what are the chances that that will exactly be the turnout in 50 years? I think the possibility is very low. But we are engineers. We need to make those assumptions and we need to move forward. We cannot just stay here and say, because we have an uncertain future, we don't do anything today. No, that's not what I advise. We should proceed with the practices and procedures that we have today, but we also need to be aware that all those projections are only assumptions so that our systems are developed. But we also need to add some flexibility because our assumptions might not be true 100%. And we need to modify our systems to compensate for that deviations from our assumptions. That's how I look at it. I hope I provided a fairly relevant answer to your question.
Thank you so much. Yeah, please.
Hi, first of all, thanks for your great presentation. I have a question about X radar accuracy. Especially in humid zones like Europe. Is that really accurate? Is that one of the best ways that we can use for measuring the rainfall? And also I have a question about satellite products that you said. One of your co-workers recently works on that. Because in Iran, we checked that satellite products in north of Iran, and it didn't work really well. And we realized it had a lot of uncertainty, and the validation factors fail in that region. I wanted to know what about X radars because it's really new for us.
Sorry. Error range? Well, I don't really know. The error range, I mean, you saw all these different error sources. I mean, all of these impacts are measured, obviously. There is something written here, wet radon. There is a kind of spherical cover on top of the radar. And when it rains, it gets wet. And as soon as it gets wet, the measurements are also affected by that. So, certainty and uncertainty of radar data, that's a matter of calibration. Because when you radiate your beams and they reflect back to the radar, doesn't mean that you have measured the rainfall. It means that you have a bunch of data registered, recorded somewhere. And I don't know those terminologies, honestly. What scientists do is that they take those data and they match it with tipping bucket measurements from the same area. And they ask the AI models to translate signal quality received from the reflections into the rainfall intensity data. So, how accurate your X-band radar is, it depends on how well it is calibrated against existing tipping bucket data. If you are not 100% free from tipping bucket data, you cannot get rid of them. They will still be there. You will need to use them because you need to calibrate your radars based on them. And of course, this is also a matter of discussion because you assume that the registered rainfall by a tipping bucket gauge is a true measurement. But tipping bucket in itself, it has its own error sources and uncertainties. But that's the assumption, the engineering assumption people make. So the rain measurements of an X-band radar cannot become much better than a tipping bucket radar. The only advantage with X-band radar is that you can take one tipping bucket gauge and multiply it by 100 or 200 to cover a larger area without actually installing the gauge. Because if you can find a relationship between signal quality in the specific location that you have for tipping bucket, you can replicate the same in other blocks as well. So you can predict the rainfall intensity in other zones. That's the advantage. So talking about the precision of X-band radar, it really depends on how well you have calibrated your signal data against
I just want to mix two questions in one. Because climate models have a lot of uncertainty, and if we use a data set which is not certain, like this one, we makes it double, And I wanted to know, is that reliable or not? And the second question is about the mitigation and adaptation techniques. We know about the problems and challenge that we will have in the future, but I think, as far as I know, I should say, the mitigation techniques are not maybe that much practical yet. I think we should focus on that part more. How can we make the urban plannings, I don't know, permeable more, or how can we make it match with the climate change that we will face in the future? I think there is a gap in here. We have a lot of research, but in real world, at least in our country, we cannot see maybe that much projects related to climate change adaptation and mitigation. Yeah.
When it comes to uncertainty, your first question, even when we work with our hydrodynamic models, if I can find, all our models that we work today are based on catchment area and runoff coefficient. Right? I mean, that's what we use. That's what we call the rational method. The rational method. You multiply rainfall intensity with the existing area and the runoff coefficient, and you assume that you have a runoff. Just think how simplified that approach is with respect to the real world hydrology. I would say it is too simplified. It's oversimplified. There is a saying among the modelers. They say there is no correct model, but some of them are useful. That's kind of the approach we have. Of course, we have all these uncertainties. I mean, even if you do not use radar data and use tipping bucket data, this runoff coefficient here, this is a headache. I mean, it is an oversimplified concept that you implement in your calculation. You don't really have another model, but that makes it much more complicated than it already is. So uncertainty is kind of inbuilt within this science. It is not a rocket science. We are not planning shuttles sent into space. That will require very precise calculation. In the field of urban hydrology and drainage, that's the mainstream. I mean, you have the uncertainty and you need to make assumptions to move forward. Otherwise, you will be stuck. You cannot move. So, making these assumptions, but at the same time being aware of the fact that these are uncertain, that's the key. And as I said, flexibility is very important. When you design your system, you always should think about how can I modify this within 10 years, within 20 years. Is it modifiable or not? Think about flexibility. That's the main thing. When it comes to climate adaptation, don't think that it's only an issue in Iran. That's everywhere. You need to, as we discussed, we need to have a dialogue with our inhabitants. I think if they understand the problem, they might take actions on their own, or sometimes it works. There is a project run by one utility company in the city of Mohammad, Sweden. The name of the project is We Together Make Space for Water. That's the name of the project. What they do is that they move to different neighborhoods, schools, different neighborhoods, residential neighborhoods. They talk to people. They talk to landowners, landlords, house owners, and they say, okay, if you just remove the asphalt in your runway and replace it with gravel, it will have this and that advantages. They try to persuade people. They try to talk to people, make them aware of different complex aspects of urban hydrology, and also sometimes monetary incentives. I don't think that will be applicable to our case in Iran, but in Sweden traditionally downpipes from the roofs were connected to the drainage network. The drains from the roofs were connected to the drainage network. Yeah, that was the case. There was an incentive that for every disconnected downpipe from the rooftop to the drainage network, there would be a monetary compensation for the owner of the house. I don't know, like 1,000 Swedish crowns or whatever was paid for that person per disconnected downpipe. So the house owner would do, okay, I disconnect my downpipe, but I still need to take care of the stormwater from the rooftop. So they have to build some kind of system for themselves. If you make this procedure kind of interesting, you make it adventurous. I mean, this is something interesting we want to experiment together within the family. Let's see what we can achieve. That could work. On the other hand, it is not 100% compliable with living in skyscrapers and high-rise buildings. This is more like villa mindset. You know what I'm saying? So these are kind of the issues that we need to think about. If you have a block of neighborhoods with 4 different high-rise buildings, what should you do there? I mean, what are the blue-green implementation alternatives? Do you have any alternatives? Maybe in the common yard in between to do something? In my neighborhood, that's the case. We have 4 or 5-story buildings around, and then we have a common yard in between. And in that yard, we have a stormwater pond, a dry pond we have implemented. So the water, the runoff is retained in that small pond before it is discharge of the municipal drainage network. I mean, these are alternatives, but people need to be aware that these are needed. These are not just for aesthetic purposes. These are actually needed, and they have an infrastructural functionality. So communication is very important. That's something that we need to bear in mind.
I have to admit that I have never talked so much in my life before.
Okay.
I'm obviously being a talkative person.
Sure. Pleasure. Go ahead.
Regarding the Quran, we have two books before. One, as you mentioned, Adaptation, and the second, to which are attributes. You didn't mention that, I guess, because that was out of the domain of the presentation, right?
I think charging aquifers, I don't know how relevant it is when it comes to urban spaces. I think flooding in natural catchments and watersheds, that has a different kind of approach. And I can understand that charging aquifers could be part of that. But when you are in a city with lots of impervious surfaces, yeah, I don't know. I don't really know. I myself have not thought about recharging aquifers in case of flood. And as I said in my, I think it was the second or third slide, when you have extreme events in urban hydrology, not environmental concerns are valid anymore, and not, let's say, drainage in itself is of importance. The only priority when it comes to these extreme events is the resilience, is to make your city function as soon as possible again. And in order to make that happen, you need to have some kind of hotspots that you can guarantee that they will work during such a catastrophic event. That is the mindset I have. So I think if one's life is in danger, probably that should be our first priority. And thinking about the amount of pollution that is kind of discharged into our natural environment in case of extreme flooding, I think that is irrelevant to discuss when it comes to these, extreme events. That is an issue here. Of course, when we are talking about drainage at service level, at design rate level, we need to think about stormwater quantity, flows, and also quality, because these flows are discharged into our natural environment, and they carry lots of pollutants, and those need to be managed in some way. But when we are here, when the lives of the citizens and inhabitants are in danger, I think the priorities should change. That is how I see this.
You mentioned that you and your team are trying to increase that 63%.
Yeah.
Yes. What kind of action are you trying to take?
I think this should be answered by the people who, my colleagues who have hands-on worked on these AI training models. But one of the options we have, as our friend mentioned, we could increase the amount of simulations that we have, the data. I mean, 3 months of data, I realized today, after we carried out this study, I realized that it is too little data. We need to have a much larger pack of data to feed into the machine learning process. 3 months, no, probably a year, I don't know, 40 months, 60 months, something like that, as much as possible. Of course, it has its own challenges, but we see it as kind of one-time investment. I mean, as soon as you have a running model, then you could use this kind of machine learning models.
I'm going to check that in 36 dimensions. You meant 36 visuals.
I was talking about optimization space, I think. Right? Here. Yeah, I said we have 30 catchments, and each of these catchments, they could be transformed into a blue-green right? So we had 30 different possibilities to work with, to find the optimum. When you have 30 variables, change and find the optimum to have a space that is 30 dimensions. Of course, it is not imaginable. We cannot imagine more than 3 or 4 dimensions. But in terms of optimization language, that's how it is used. I mean, if you have 30 catchments to play with and transform into blue-green so that you find an optimized scenario, you have an optimization problem that has an
Thank you so much. First of all, for Salar, for accepting to be here. I really appreciate your time, your encouraging. Yeah, thank you so much. Also, the attendees who are in person and online. Let's cheer, Salar.
Oh, thank you so much. Yes, I will put this in my office as a souvenir. Thank you so much. Thank you. For those online who want to use this
Mark. And on this Mark said, what is Wednesday webinar? And it has a hashtag and a 2024 series, and there is a logo of Toosi University on the book. So thank you.
Just now, I would like to take time a little bit to introduce our next event. Perhaps it will be also interesting for audience here and those who are attending online. Yes, just taking the present thing. Oh, you can find it. Yeah. I think we will have it somewhere in the meet soon. Yes, this is the. We cannot see it here because perhaps I do not. How can I share it? But it's on the meet. Okay, those are attending online. This is our next event, so please reserve your calendar. It will be on 8th May. The presenter will be Dr. Abulfaz Irani Rahabi from the EVEC Switzerland, discussing on Alp lakes, advancing lakes, let's say, research and management through the integration sensing systems. It will be our pleasure to have you in that session as well. I do not take your time anymore. Just 2 more points. First of all, we will have a group photo for those who are attending here, so that the online attendees may open the, let's say, the turn on the cameras as well. We will take the snapshot from them. And before ending the session, actually today is the Mother Day in Iran, and let's say I would like to take this opportunity to wish all mothers all over the world happy days. But I would like to also to take this opportunity to show my solidarity and empathy with the mothers, or let's say Palestinian mothers, who are let's say suffering during the 75 years, and especially during the last 3 months, losing their beloved ones. So, as a solidarity with other people all over the world, and to show our respect and empathy with them, let's have the moments of silence, and after that we will go for the group photo. Okay, thank you so much all. Have a nice day and goodbye. I'm just